Today we're going to learn about reaction profiles. And a reaction profile is a graph to show how energy changes in a reaction. So, if we remember from last week, we were learning about exothermic reactions, and we had this picture of an exothermic reaction. So let's draw that out again. So we have our reactants, which were methane plus oxygen, and our products, which were water and carbon dioxide. And I said that we can think about the amount of energy these have similar to the amount of energy in a battery. So if we have, remember that for this one, in our reactants there was a lot of energy, and then in our products there was less energy. Right? And we said that when the energy goes down during the reaction, that energy needs to go somewhere, and it is released to the surroundings, which is why when you burn methane in oxygen, you get warm, because energy is being released from the reaction and you get warm. All right. So we're now going to try and make a graph that shows this. So if we think about this level here, all right, is this much, and this level here is this much. Okay, now we can start to draw this as a graph. So if I draw in axes like this, all right, then I can say, well, that on this axis I am measuring the amount of energy. Okay, because remember I said that the reactants had more energy, the products had less energy. And on this axis here, well, I'm going from my reactants to my products. So this axis here tells me about how far along the reaction I've gone. So when I'm over here, I haven't started my reaction. Over here, I have finished my reaction. So we call this axis the progress of the reaction. Okay, so our graph is almost complete, all right, but there's one more thing that we need to think about. And that is, how do we connect these two levels? Okay, so you might think, well, it just goes straight down, all right, but it doesn't do that. All right, what actually happens is that I have the amount of energy in my reactants, and then first of all, the energy goes up, and then it goes down. Okay, so what's going on here? Well, what we need to do is, when we have our reactants, we need to first put a little bit of energy in to get it up to here, and then the energy will go down to where we have our products. Okay, so we can think of it like this. Imagine that you are in a car, okay, and you are up here, okay, you're quite high up, and you want to get down here. You want to get home down here. All right. Now, when you are at home, you're going to be lower down than when you are where you are at the moment. However, to get home, you first need to go over this hill. All right, and then you can go down to where you are at home. So once you're down here, you will be lower than you are here, but first you need to go up over this hill. All right, and that's what's happening in our reaction. So this is where we start, and this is where we finish. But in order to get there, we need to go up over this hill, and then we're at home. So what we have is this here is what we call the activation energy. Okay, so this is called the activation energy. Okay, and what it does is, it is the energy required to start the reaction. Energy required to start the reaction. So, the way you can understand this is, well, let's suppose that I am in my lab at school. Okay, so this is the room here that we are all in, right? And this is me at the front of the classroom, all right? And so in the room here, there is air. And in the air, there is oxygen. All right. And at the front of my desk here, there is a little tap. And that little tap, if I turn it on, okay, a gas comes out. And that gas is methane. So imagine I turn on the tap and methane comes out. All right. Now remember, oxygen and methane are the two things that I need for my reaction. All right. So what I've got now in my room is I've got oxygen and methane. Now, will those two gases immediately react? The answer is no. Okay, they don't. So if I turn the tap on, nothing will happen. Okay, you'll be able to smell the methane in the room, but apart from that, there's no reaction. So I just have oxygen and methane together. What do I need to do in order for these to react with each other? I need to take a match and I need to set fire to the methane. Okay, and it's that bit of energy from the match which starts the reaction. So that bit of energy from the match, that is the energy that starts the reaction. Okay, that's the activation energy. All right. So you can also think about it. Let's say this piece of paper here. All right, this piece of paper. I no longer need this piece of paper, so I'm going to burn it. Right? Now, this piece of paper will burn very easily. Okay, but it's not burning now, is it? What do I need to do in order for this piece of paper to burn? In order for this piece of paper to burn, what I need to do is I need to, first of all, give it a bit of energy. Okay, so I will need to give it this bit of energy here. All right, and that will start the reaction. So this bit of energy here provides the activation energy. Okay, so if we carry on now, we just need to mark on one final thing on our graph, which is that we have from here down to here, that is our energy change. Okay, and you can see that for this reaction, the energy change is negative. And remember, that makes sense because if the energy change is negative, energy is lost. Where does the lost energy go? It goes into the surroundings to make you warm. All right. So what we can do now is we go back to what we had last week. Now you might not have space for this, so don't worry if you don't have space. You can add it to your flashcard for your exothermic reaction. So the fourth thing we can write about an exothermic reaction is that the reaction profile looks like this. So we have energy against progress of reaction. And we start up here, we end down here, and it looks like this. All right? And we can say that this here is the activation energy. That's the activation energy. And we have also a negative energy change. Okay, so that's exothermic. What about endothermic? So in an endothermic reaction, now I'll just do it for any general endothermic reaction. So if we have the reactants turning into the products, we had the opposite situation. So we had, if we imagine the energy stored in our reactants was this much, then in an endothermic reaction, the energy stored in the products is going to be higher than that. Okay, so I've gone from this much energy to this much energy. So if I now do the same as I did before, and I draw a set of axes around these two values, okay, which is the same as before, so this is the progress of reaction. And this is the amount of energy. Okay, and it looks the same. So we have, when we go from the reactants to the products, the first thing we do is we go up in energy and then we come back down. Okay, and we can say that this is the activation energy, and this is the activation energy, and this is the energy change. Which is positive. Yep, because I've put energy in to the reaction, so the energy's gone up, so it's a positive energy change. So if you think again about your, if you lived, so your house here was on the top of a hill, all right, and this is your car. Okay, if you lived at the top of the hill like that, what would happen? Well, the car would just immediately roll down the hill, all right, and you wouldn't be able to stop it. But because we've got this this barrier here, all right, what this means is that your house looks like this. All right, and your car can go here. So even though your house and your car are really high up, much higher up than here, it won't just go down. So it can't roll down to here, because in order for that to happen, it first needs to go up. All right, so it's like a barrier that stops the car rolling down the hill. Okay, and it's the same thing here. Even though your products are up here, because there's this barrier, they can't just roll down to here. All right, now we can add this to our endothermic summary. So we have number 4, our endothermic graph looks like this. This is progress, and this is energy. And it looks like this. Okay, with our activation energy and our positive energy change. Okay, what I would like you to do now is answer the questions on this sheet here. All right, so this is how you need to answer these questions. Right? So for the first question, I've given you the steps. So you need to label the axes as I've been labeling them. Add the symbols for the reactants and the products below the horizontal line. So remember these here. This is the reactants. And these are the products. So you need to take these symbols and you need to add them underneath these lines. Label the overall energy change. So I've just been doing that on my reaction profiles. So you need to draw an arrow for what the overall energy change is. And you need to add a curved line to represent the course of the reaction, like the curved lines that I've been adding onto mine. All right. Number 2, state that the following processes are endothermic or exothermic based on their reaction profiles. In each case, explain your choice based on the relative energies of the products and reactants. So I'm going to look at my first reaction profile. Okay. Now, does that reaction profile look like this one for endothermic, or does it look like this one for exothermic? Okay. Well, I think it looks like this one. So I'm going to say that this is an exothermic reaction. Okay, and I'm going to explain it based on the relative energies of the reactants and the products by saying that the energy of the products is lower than the energy of the reactants. And it's as easy as that. So I want you to do the same for these two. And then, on the next page, you need to draw a reaction profile for each of the following processes. So, you do that by drawing the axes, like I did. Okay, label them. Progress of reaction and energy. Now, the overall energy change here, okay, this is positive. So if it's a positive energy change, does that mean it's going to be this or this? Well, I've written here, positive energy change for my endothermic reaction. Okay, so I know that it's going to look like this. Okay. Now down here, I've got H2O liquid, and up here I've got H2O gas, because those are my reactants, those are my products, and then I've got the line between them, looks like that, and then I'm going to label my overall energy change, and the overall energy change is the difference between the reactants and the products, that there. Okay, so that there is plus 15 kilojoules per mole, which is just the units for energy we're using at the moment. Okay, so then you need to do the next two there.